All right, welcome everybody. Today we're going to talk about lesson number 20, and this is another set of chapter 2 calc connections where we're going to talk about something called concavity and points of inflection. And again, it's possible that you may have heard those words before in some context. Just like when we've been looking at polynomials so far, which is what we've been looking at for the last couple of sections, you've been able to tell me where are the x-intercepts, where are the y-intercepts, what's the end behavior, where is it increasing, where is it decreasing. So yet another thing you're going to be able to add to the list is your ability to tell me where is the graph concave up or concave down, and where is there a point of inflection. So first, let's go ahead and define concavity. So there's lots of different ways to think about concavity, and I'm going to show you as many as I can think of. So basically, in layman's terms, concavity is the direction in which a graph bends. A graph is said to be concave up at a point if the tangent line to the graph at that point lies below the graph in the vicinity of the point, and concave down at a point if the tangent line lies above the graph in the vicinity of the point. So for example, again, let's look at the section here that's considered to be concave up. Notice that for every tangent line you could draw, they would be underneath. Whereas if you were to look at the section that's labeled concave down, every tangent line that you would draw would lie above the region. So again, that's one way to think of concavity, not just in terms of which way does the graph bend, but also in terms of where the tangent lines are. Again, if the tangent lines would all be above, that's how you know that the graph would be concave down. Whereas if the tangent lines were all below, that's how you know that the graph would be concave up. Lots of other different examples and lots of other different ways to kind of think about concavity. And this would be an excellent slide to refer to as you try to do homework 20 tonight. So the way that you can again describe concave up versus concave down is, for me, any place on the graph that's concave up is where you would be able to hold water, where anywhere that the graph was concave down was where the water would start to spill out. So if you take a look at this first example here on the top left, notice that that's just a quadratic, which looks like x squared plus 1. If I was to try to fill this graph with water, it would hold water the entire time, which is to say that the entire polynomial would be considered to be concave up. Look at the second graph. If I was to try to put water into this quadratic, it would spill out the entire time, which means that the entire graph there is concave down. Can a graph change from concave up to concave down and then back? Absolutely. The locations at which it does change is an important location. Let's take a look at the bottom left here in blue. Notice that the first region of the graph up until the dotted line is where the graph would be concave up. Again, here is where you would be able to hold the water. Then at the dotted line, now it switches, and here's where the water would start to dump out. So that would be concave down. And then the graph changes again, where you'd be able to hold the water. So that is where the graph would now be considered to be concave up. These represent polynomials, which again is what we've done in sections 2.1 to 2.5. In section 2.6, we're going to talk about rational functions, where the parts of the graph are not all connected, and you can still classify those different branches as being concave up or concave down. So notice here in the top right is another example of concave up. Even though it's a little harder to imagine that piece of the graph holding water, it certainly would. Whereas here, the graph would be concave down, meaning that the water would start to dump out. Again, if the whole water thing isn't helping you, think about where the tangent lines would be. Because of the fact that the tangent lines would be underneath on the left, that's how you know that it's concave up. The tangent lines would be above on the right, so that's how you know that it's concave down. So everybody should kind of start internalizing for themselves what their own definition of concave up and concave down is. And those are the only two choices, concave up or concave down. Then again, the bottom right-hand corner here, this is important when you're being asked to graph something that has a specific concavity, because there's two different ways that you can be concave up and two different ways that you can be concave down. So you can be concave up and decreasing, in which you look like this first box. Then you can be concave up and increasing, in which case you look like this top right box. Then you can be concave down and decreasing, or you can be concave down and increasing. So again, I think that this slide in particular, and perhaps this bottom right-hand part of the slide, is going to be the most helpful for you in the homework tonight, as you not only try to identify where things are concave up and concave down, but also as you try to sketch some graphs for yourself. So again, yet another way of thinking about concavity. So concave up is when the slope of the tangent lines increases. So if you take a look at this example over here, again, not only are all the tangent lines underneath, but the slopes of those tangent lines are increasing. So if you were to find the slope of tangent line A versus the slope of tangent line B, I'm sure you could agree that the slope of tangent line B would be much steeper, and they're both positive. Concave down, you can talk about that's where the slope decreases. So again, if you were to consider the bottom right-hand side here, if you were to look at this tangent line A versus this tangent line B would certainly have a less steep slope while they would both be positive. Again, that's another way of thinking about it, whether the slopes are increasing or decreasing. So you've now seen at least 3 or 4 different ways to define concavity. Again, you're going to go ahead and pick the one that makes the most sense to you. And then where the graph changes from either concave up to concave down or vice versa, that is called a point of inflection, or sometimes just an inflection point. And again, that is where the graph changes concavity. So here are 3 examples. So in the first example, the graph starts being concave down, the water is dumping out. At a certain location, you now would be able to hold the water and the graph changes to be concave up. So that would be considered an inflection point, or again, a point of inflection. In the middle, here the graph is concave up, then you reach a point where the water starts dumping out. So that would be another point of inflection. And then finally, what if you were to start concave up and then change to being concave down? So again, these are just 3 of the ways that you might see these inflection points. There are others, but again, it's where the graph changes from concave up to concave down or vice versa. So what kinds of things are you going to have to do with these problems? Let me just go ahead and change to my pen here. Okay, so you're going to have to be able to describe the intervals where the graph is concave up or down, and then locate any points of inflection. So for the first couple, I started it nice and simple for you. I even labeled it concave up, concave down, and the inflection point, so you could kind of get an idea here. And again, this should look very familiar in terms of what we've been graphing lately. That is certainly a polynomial. So for any graph that we've done so far, you would be able to go back and identify these regions. Here's the thing though, once you get to calculus, there is a procedure. How do you find out exactly where the graph is concave up and concave down? That's a little bit too advanced for us right now, so we're just going to talk about it theoretically. So you're guessing at a certain point, but really you're just giving an educated analysis based on the picture in front of you. So where is the graph concave up? Where is the graph concave down? And then the point of inflection. First, a note about concavity. You are going to give your answers using all parentheses, similarly to the way that you use all parentheses for increasing and decreasing. Once you get to the point of inflection, how do you know whether it was concave up or concave down at that exact point? You don't. So that's why you give your concave up and down as using parentheses only. So I don't really care, the order that you list them in. Here, I'm going to start by listing the point of inflection, which I call the POI for short, and that looks to be the point 1, 2. And then some people always like to do their concave up first or their concave down first. You can also just go from left to right. So in terms of the graph being concave up, it looks like the graph is concave up everywhere right up until the point of inflection. So that would be from x equals negative infinity to x equals positive 1. So I'm going to use CU for concave up, and that would be from negative infinity to 1. Then the graph would be concave down everywhere else, which would be from the x value of the point of inflection to the biggest x value, which would be infinity. Again, if you put the concave up intervals together with the concave down intervals, that should include all the real numbers. And again, you're always going to use parentheses for concave up and down because of the fact that you don't actually know what is happening at the point of inflection. Here in number 2, same question. And again, if you look, I've labeled it for you. You have to make sure you understand what you're looking for in the next couple of examples. So again, I'm going to go ahead and start by labeling the point of inflection, which in this case would be 0, 0. Then it looks like the graph is concave up everywhere here, all the way up to the point of inflection. So I would say that the graph was concave up from x equals negative infinity to x equals 0. Then I would say that the graph was concave down from 0 to infinity. And again, for these examples, it doesn't really matter what order you list them in. Certainly once you get to the homework or a test or quiz, you'll give the answers where I ask for it. So let's just do several more here because we want to see all the different possibilities. So notice here in number 3, this certainly is not a polynomial. It's kind of just some random graph that I made. And notice that instead of giving you actual numerical values, you have just letters. You can assume, though, that the graph is going to go to negative infinity and infinity in terms of the x values. So determining the points of inflection to start is actually, I don't think, a great idea. So I'm just going to go ahead and go from left to right in terms of the concavity, and then I'll list the points of inflection at the end. So to me, it looks like the graph starts being concave up all the way until I get to B. So I'm going to say that the graph is concave up from negative infinity until I get to B. Then it appears that instead of the water being held, now it appears that the water is being dumped out. And it appears that the water is being dumped out, dumped out, dumped out, dumped out, all the way until I get to E. So I would say that the graph is concave down from B to E. Then notice that as I continue, the water is still being dumped out, dumped out, dumped out, and it kind of looks as though it's being dumped out all the way until I get to G. So that's a second location where the graph is concave down, and I would say that that's from E to G. You can use a union between those intervals if you want to, but you don't have to. It really doesn't matter. And then again, once I get to G, now it looks like I'm able to hold the water again. And if you assume that the graph follows a similar track off to infinity, I think it would be safe to assume that the graph was concave up from G to infinity. So again, even if there are no numbers, you should still be able to analyze a graph. And then if you're going to label any points of inflection, a point of inflection can only be a location where it changes from concave up to concave down. So one of those locations was at point B. The second of those locations was at point G. So my 2 points of inflection in this case, and you can have as many as the graph, has, would be at B and G. And since we don't know what those points are, we're just going to go ahead and call them B and G. So let's take a look here at number 4. And at any point, if you're feeling confident that you know what you're looking for, you can feel free to pause and try it. Otherwise, you can go ahead and listen as we go through these together. So again, think about all the things you'd be able to tell me about this graph already. It's clearly a polynomial. It's clearly a cubic polynomial because it has 3 real roots. Those roots appear to be at -3, -1, and +1. And because you're crossing the graph at all of those places, you would be able to tell me that those were all multiplicity 1s. If I was to ask you in terms of increasing and decreasing, I think you'd pretty easily be able to tell me that the graph was increasing from negative infinity to -2. That would, of course, be the relative maximum. Then the graph would be decreasing from -2 to 0. That would, of course, be the relative minimum, which in this case happens to also be the y-intercept. And then the graph would be increasing from 0 to infinity. Notice that because technically any polynomial has arrows on both ends, there would be no absolute maximum or minimum. There'd only be relative maxes or minimums. And again, you can also call those local maximums or minimums. In terms of the end behavior, you're used to calling this down up. But again, I do want you to start getting used to that infinity notation, which I do ask you to use tonight. So if you were going to describe the right-hand behavior of this graph, you're trying to tell me what happens as x goes to infinity. And as x gets bigger and bigger and bigger, y is also getting bigger and bigger and bigger. So as x goes to infinity, f of x goes to infinity. If I was asking you for the left-hand behavior, you're trying to tell me what happens as x goes to negative infinity. And as x gets smaller and smaller and smaller, it turns out that y, or f of x, gets smaller and smaller and smaller. So again, I do want you to start getting used to using that infinite notation. It's going to become especially important in section 2.6 and also in chapter 3. That was kind of just a good review about general polynomial analysis, which again, you're going to need that tonight as well. But let's go ahead and put back on our concavity glasses and look for any potential points of inflection. So again, if you're not sure about the point of inflections right from the get, I would go ahead and just kind of go from left to right. So let me kind of switch to my highlighter here for a second. As I'm looking at this graph, okay, and I go ahead and try to draw what I think is a logical piece. To me, that there, that's highlighted now in yellow, looks like a location where the graph is entirely concave down, meaning that any water that you would try to put would dump out. And again, another way of describing that would be any tangent line that you would draw to the curve anywhere between negative infinity and negative 1, the tangent line would be above, which means that means that's where the graph is concave down. So let me go ahead and go back to my pen here. So I'm going to go ahead and start by saying that the graph is concave down, where I highlighted it in yellow, which would be from negative infinity to negative 1. Then it looks like the graph would now start to be able to hold the water. The tangent lines would be underneath. So now the graph is concave up from negative 1 to infinity. And because of the fact that there is a change in concavity, I could say that the inflection point or the point of inflection, it doesn't matter what you call it, would be there at negative 1, 0. So again, you really do want to add concavity and inflection points just into your general list of polynomial analysis, which is exactly what you're going to do tonight. Couple more here, and again, at any time, feel free to pause and try it if you feel like you know what you're looking for. So taking a look here at number 5, if I was to start at the left and just kind of go through and think about my tangent lines, to me, this part here that I've highlighted in green, to me, that looks like where the water would be held. So I'm going to go ahead and say that this graph is concave up from x equals negative infinity to x equals negative 1. Then it looks like the water would be falling out everywhere between negative 1 and 1. So I'm going to go ahead and say that the graph is concave down from negative 1 to 1. Then it looks like you would start being able to hold the water again. So there's another interval of being concave up, and that would be from 1 to infinity. And again, here's where, you're probably wondering to yourself, well, how do you know that it's happening exactly at negative 1 and positive 1? In terms of right now, you don't actually know for sure. I'm asking you to just give a reasonable estimate. What if you think that it still was concave up until negative 0.75 or negative 0.5? For now, I would accept anything that's reasonable. Like I said, once you get to calculus, you're going to definitively find those locations using a series of tests and formulas. But for now, I'm just asking you to do the basics. So just go ahead and choose reasonable estimates. And then points of inflection, in which case there are 2. And again, it's where the graph changes from negative concave up to concave down or vice versa. So there would be 2 locations at negative 1, 0 and 1, 0. Finally, take a look here at number 6. Hopefully this looks familiar. This is the graph of, again, what's called a rational function. That's what we're going to be talking about for the next several days. The concavity looks a little different, okay? So it's not going to be as perfect as holding the water and dumping the water as they've been so far, but you're still going to be able to tell me about the concavity. So because this is a rational function, you may or may not remember that there are asymptotes. So there's an asymptote here at negative 1, and there's an asymptote here at 2. Whenever there's an asymptote, you're going to have to break in terms of increasing, decreasing concavity. So you have to keep that in mind. Even if your graph was somehow concave down the whole time, you would still have to break for asymptotes. So let's go ahead and look at the first piece of the graph. And again, if your only options are concave up and concave down, any tangent line you would draw would be above that piece, which I think it's pretty safe to say that that piece would be concave down, which would be from x equals negative infinity to x equals negative 1. Then if you pick up on the next piece, okay, again, it's not super curvy, but I think that is where you'd be holding the water. Again, the tangent lines would be underneath. And then I actually think that changes once you get to 0, 0. I now think you'd be dumping out the water. So I think that it's safe to say that you're concave up only from -1 to 0. Then I think you change to being concave down, so from 0 to the asymptote. Then for the final piece, I think it would be safe to say you're holding the water again. The tangent lines would be underneath. So that's another location of being concave up, which would be from 2 to infinity. And again, generally speaking, when you add up all your levels of concavity, it should be all the real numbers. And then the point of inflection is where the graph changes from concave up to concave down. And a point of inflection, by definition, has to be a point. So in this case, the only point of inflection would be 0, 0. Even though at x equals 2, it changes from being concave down to concave up, that's an asymptote. By definition, an inflection point has to be a point. So those examples, I think, are enough for you to do homework number 20 tonight. And homework number 20 is a worksheet in class notebook. It asks you not only to analyze a polynomial in terms of this new vocabulary, but also to just think of it in terms of all the vocabulary that you know so far. And then you're also going to get your first chance to see what would be an example of a free response AP question. Remember, when it comes to the calculus AB test, half the test is multiple choice and half of it is free response. So you're kind of starting to see what those questions would look like. So thanks very much for tuning in, guys, and we will catch you next time.